All right, so we've got this mixture, and the mixture is at equilibrium, and we've got these concentrations of these different substances, and there's the chemical reaction, and it shows an equilibrium there, and it wants to know what the equilibrium constant is. So the equation that we're going to be writing here, I got to turn something on first, just a sec. There we go. The equation is going to be K is equal to water to the second, chlorine to the second, divided by hydrochloric acid to the fourth, and oxygen to the first. So we can just kind of plug and chug here. It says we've got 1.2 times 10 to the negative third chlorine, so 0.0012 raised to the fourth power times, where's the oxygen? 0.00038, and then that's my denominator, and my numerator is 0.058 squared times 0.058 squared. All right, so let's see if I can plug this in. 0.058 fourth divided by 0.0012 to the fourth divided by 0.00038. So this is a big number. 1.4 times 10 to the 10th. We good with that?
I'm good with that.
Okay. The following reaction is not in equilibrium. Determine the value of the Q for the following reaction given with the equilibrium concentrations. The K value for this reaction is 150. What will the reaction need to do to return to equilibrium? Okay, so we basically treat this exactly the same. We're just answering a different question. So Q we equal to NH3 squared and N2 and H to the third. So we've got 0.4666 times 0.14 squared, 0.62. I don't know why I put squared. Let me erase that. Cubed. 0.62 squared. So I've got 0.62 squared divided by 0.466 divided by 0.14 cubed. 300. So this works out to be 300. Okay, so what's the equilibrium going to do on its own, knowing that the Q value is 300?
It's gonna turn the NH3 back into N2NH2.
Yeah, I've got my denominator is too small, so I'm going to make more denominator. And I do that by tearing apart the ammonia molecules and turning them into nitrogen and hydrogen. Okay. Look up the amino acid glutamic acid, draw its structure. What is its Ka value? What is its Ka value?
So I did have a few questions on this one because I could only find a pKa value, and
That's fine.
okay.
They're the same thing, almost.
Okay.
Uh, okay, so first thing we're gonna do is draw the structure. So all amino acids start with that. And then the side chain comes off of this carbon. It's always going to come off that carbon. And for this instance, it's a oops, carbon. Is it 2? You know what? This is probably not a good way to do this. Let me do it like this. I don't have enough space otherwise. All right, CH2, CH2, CH, and then I'll write NH2 here. And then we can do a C double bond OOH. There we go. So there's its structure. So the R section is the red section, and that's what makes it glutamic acid. So all amino acids have the blue portion, but only glutamic acid has a portion that shows it like this in red. And there are many different structures that could be there, but for glutamic acid, we need this one. All right, so what do we have for Ka for that? There's a 2.19 and a 9.67. Okay. If you had glutamic acid, what would be the concentration of HB? Okay, so these are pKa values. I'm sure if you looked hard enough, you could find a straight up K value for that. But we're going to find out when we talk about acids and bases that this P is a mathematical construct and it means negative log. So when I take the pKa, what I've done is I've taken the Ka and taken the negative log of it. It just gives you a nicer number, a number with no exponents, no 10 to the anything. So how do you go backwards from this? Well, the opposite log and 10 to the x, they interchange with each other. You go back and forth with that. So I take whatever this number is and I make it the exponent for a 10. So negative 0.7 or 10 to the negative 2.19. All right, so what you would need to know is which one of these numbers would be more relevant in this particular circumstance, and the answer would be the 2.9 number because this is an acid, and you're right, we didn't talk about this in class, but the lower the number, the more acidic it's going to be. So the second number is the fact that all amino acids have one acid right here, but since this is glutamic acid, it's got a second acid on its side chain. So because it has two acids, I'm going to be using the lower number. So then what we're saying is the Ka value for this is 10 to the negative 2.9. That might be frustrating for you, but whatever. You can do that. Exponents can have decimal places. It doesn't matter. So we know what this is equal to, and this whole thing here, the glutamic acid, an easy way to write it to make it more palatable mathematically is there's the acid part, and that's the entire rest of the molecule. So in our instance here, this is my acid, and everything else is the molecule. So I'm going to write HA and then H plus and A negative. I was told that this value here is 0.25, and I don't know H, but I know it's A value, and I know that the A value is also the same number, but I don't know what it is. So this is that instance where we do the x is equal to the square root of, in this case, 10 to the negative 2.9 divided by 0.25. You might have some issues with your calculator, like knowing how to type this in.
Good question.
Yeah.
Would it be divided by or multiplied by 0.25?
Oh, you're right. It's multiplied. My bad. Eraser divided dot times. So 10 caret negative 2.9 times 0.5, close parentheses, and just to be safe, I'm going to parenthesize the exponent. Perfect. So I get 0.025. So that's going to be the concentration of X, which in this case is going to be equal to the concentration of H+, which is what we were looking for. Okay. What will happen to the concentration or the equilibrium under these following conditions? So pressure, the total pressure increases. Okay, so what does Le Chatelier say happens when you stress a system? A system
It wants to de-stress.
So whatever I did to it, the reaction wants to undo it. So if in the container the pressure goes up, what will the equilibrium try to do?
The equilibrium towards the product.
That's not what I asked.
Okay.
If the pressure goes up, what's the equilibrium going to try to do? Anybody? Bueller? The pressure is going to decrease, right? The pressure went up. The reaction is going to try to decrease the pressure to reverse what you did. So Ethan was correct. What has to happen is it's going to shift towards the product side, but that wasn't the question. The question is, what's the reaction going to do? So it's going to act to decrease pressure, and it's going to do that by shifting to the products. Why? Because on this side there are 4 gas particles, and on this side there are 2 gas particles. And pressure is about small things, or about something hitting something else. So if I decrease the number of particles hitting, then I decrease the pressure. So shifting to the product side will reduce the pressure. Okay, so my next stress here is nitrogen is introduced to this reaction. So what's the reaction going to do? Take away N2. So the pressure is going to go down. So I'm going to reduce the amount of N2. And to do that, I will also shift to products. So I'm shifting to the products because it's consuming the nitrogen and thereby getting rid of some of the nitrogen that was added. All right, so hydrogen is added, or sorry, hydrogen is removed. So what's the reaction going to do? Replace it. Replace the missing hydrogen. So increase the amount of hydrogen. So that means I'm going to have this shift to reactants. Because if I shift it to the reactants, then I make more of the hydrogen that was lost. And that's it.